Hey, so last lecture before the final exam review lecture, not a lot of new topics covered here, mainly review of VRT, and then some general wrap-up comments about SIM. Um, Structure here, there's today, there's Open Lab still available this last couple weeks here for project questions. Of course, there's Thanksgiving break the end of this week, so no class on Thursday. Course evaluations, I believe, have been released. So there's a link here to the full course evaluations, but you can also find it in the navigation bar on the top left in Canvas. So it should say right like home course evaluations. There's the next lecture. So the sort of last lecture, last time I'll stand up here is in this semester will be on the Tuesday of next week, and that'll be our final exam review. So there is a final exam practice that is due before that lecture, which is just samples from the previous ICAs. Add in a couple of new questions. You can take it as many times as you want. It's going to give you more points than the normal ICAs. But you also will get the highest score of all of your attempts. So just like the midterm review, there are other resources on Canvas, including practice exams, practice problems, and so on. That's in the final exam module, which will have to complete that compliance, that lockdown browser compliance for the final in order to get access to that. Then project presentations. So I will I'll be making the assignment where you upload these available very shortly. But basically, you'll have two things that'll be due next week by Wednesday. Basically at midnight. So, and I'll need them in basically then so that I can make sure that Canvas can randomly assign those peer reviews. So this is the one time where there's not going to be a grace period. Everybody's really got them in Wednesday night. And so you'll upload 10-minute video presentations to Canvas. You can record those however you like. Not everybody has to be pictured in the video. It just has to be sort of a compelling video that meets the criteria that it's on the rubric. So no longer than 10 minutes. And then you'll also have to upload a project report. Both of these are group assignments, so only one group member needs to upload them, and it'll populate it for all the whole group. There are 4 pages of content. There's a format for that, which is posted online, so follow that format. I think one of the things in the rubric is, did they follow the format? And so it'll be 4 pages excluding a title page. If there are things that you can't quite fit into that 4-page format, like you want to highlight a particular part of your model, but if you put your whole model, it bleeds over, then you can always put that into the appendix. But anything in the appendix should be referenced. So you can say, so here is, we've broken out this particular part of our model that captures these important complexities. For the full model, see figure A1 in the appendix or something like that, or even just figure A1. So make sure that the appendix isn't just sort of a dumping ground for anything that you think might be important. Anything in the appendix does have to be referenced, but you don't. So it's mainly just to give you a little more flexibility as you put that report together. And then by Saturday, your peer reviews. And so I'll be asking you for, it's normally one other presentation and one other report. Things are a little different in peerceptive, so this might change slightly, but not much than this. But you're basically going to be assigned to do one or two of these peer reviews, and then that will be the last kind of non-exam thing that you'll be responsible for. So then the final exam, that will be Thursday of next week. So that's the last normally scheduled lecture period. That's the stage one. So you can come here if you want, but you do not have to. It will be on Canvas. I'll make it available at least Wednesday, Thursday, and Friday. I'm considering just extending it Saturday and Sunday as well. So whenever you start it, you'll get 90 minutes. If you come in here, then you'll be restricted to the 75 minutes of the period here, because a lot of times the class does come in. You will have access to two-sided hand-generated formula sheets or cheat sheets, but just like in the midterm case. And then stage two, that'll be during finals week. I'll just leave that open for sure Monday, Tuesday, Wednesday, Thursday, and Friday, untimed, just like the midterm stage two, collaborative, open book, open notes, open Canvas. If there will be someone staffed here during the assigned period, which is on the calendar, but you don't have to come here. If you want to come here to meet up to work on the collaborative, as a couple of people did during the midterm, that's totally fine. But if you'd like to do it elsewhere, if you'd like to use, Discord or Slack or whatever for that stage 2, that's fine too. But just make sure you're only collaborating with people enrolled in the class. So that's the timeline there. Any questions? Okay. So let's just do a quick eye clicker just to give people who um, came in gracefully during this Thanksgiving week some credit. So I'll do this will be a short answer. And so, what is the ultimate goal of using VRT in simulation studies? So, yeah, of course, you could say it's reducing variance, but that's the proximate goal. That's how we're getting to that. So, beyond reducing variance, why do we want to reduce variance? So, what is the point of VRT? What ultimately do we hope to get out of it? So, I think you can summarize that in a couple of words. So, go ahead and do that. Get rid of this spotlight. Okay. So ultimately, hopefully, as we got from the last whole unit, it's to reduce the number of replications. And so it may not seem like it, but complex simulations, I mean, the sims we've done in this class end very quickly. But if you have to run a lot of replications of them, even the sims in this class, some of the more complicated ones would take a long amount of time. And then some very realistic sims that include a lot of complexities of a real world system that are sort of really begging for someone to analyze them with a complex tool like a sim. Those sims are going to take a very long time. And so you may not have the computational budget. So whatever you can do to reduce the number of replications is going to benefit you. So that's really the ultimate goal of VRT, is to reduce the number of replications. So that's what we're going for there. And then how do we do that? Well, we do that by reducing variance. What we mean by that is the reason we have to generate replications in the first place is to account for there's going to be variability in our output. Some of that variability just comes because we have variability in our inputs, or there's other variability coming in through disturbance inputs to our system. And so if we want to analyze our system, there's just a certain amount of variability we care about and a certain amount of sort of parasitic variability that we get. And if we can somehow account for that extra variability, then we can focus on the variability we really care about. So that's the idea here, is that we know that the reason we have to run replications is because there's always a chance that our output we could have gotten a good output just because we get good luck on that case. So we do multiple replications because we have variability, but we don't, some of that variability is just nuisance variability. And that's what VRT does, is it tries to control or account for that nuisance variability. And so we've talked about kind of 4 different ways to do that. So, we talked about CRN, which is for relative performance estimation. So if you've got 2 models, how can I possibly reduce the number of replications I need to study the difference between those models? Well, I'm going to induce a positive correlation between them and then subtract off the variability that shows up in both of them so that any variability that remains is really about the differences between those models. I can also do sort of a absolute performance version of that, an antithetic variates, where I introduce a negative correlation between successive replications so that pairs of replications from the same sim tend to sort of be on the opposite side of the performance measure I'm trying to estimate so that I can use a smaller number of replications to balance out the variability so that I can more quickly converge on that estimate. I've got then importance sampling, which is another way to do absolute performance estimation where I bias my inputs so that it stress tests the model so that I can manage to milk the model for more of those events that would normally be rare so that I can estimate how often they occur without actually having to wait for them to occur that infrequently in sim. And then control variates, where I can just look at an input that I know a lot about and the output, which I don't know a lot about, study the correlation between the input and output, and then use the knowledge I have about the input to subtract off variance in the output that is likely due to that input, so that what I have remaining is less variance, so hopefully need less replications. These three, because we toy with the random number generator, are things that are sort of simulation only. Although you could argue that if, there are ways to do things to create blocks like this CRN uh, in real experiments as well. So these are things that because we, sim only, that's because we have to access the random number generator. Down here, control variates, that's just something you can apply to any data set. And it's very strongly related to sort of multivariate linear regression. So this is kind of a hint at things that you can do with in data science more broadly. So those are kind of our four methods. So just want to kind of, this is a kind of a graphical reminder of each one of those, because this is something we haven't had a chance to practice with, but you will see these on the final. Is like, say, CRN. So graphically, what we'd expect in a CRN is we have for a given replication, it starts with a certain pseudorandom numbered seed, which will generate a long sequence of random numbers. I can feed those random numbers into two different simulations. They're shaped differently. This is one flow chart. This is another flow chart. But when I feed in the same numbers, then that can create a correlation where for this replication, let's say I get the same customer or widget order or inventory order or whatever inputs into this model as I do into this model. So even though the guts of the model are different, the driving force that the model has to react to is the same. And that means that I can ask for this pseudorandom number seed, what is the difference in performance between these two? So for the same driving challenge, how well did this one do? How well did this one do? And what is the difference between them? So now for every pseudorandom number seed, so for every unique challenge, I can then associate a single difference. So even though it looks like I'm running two sims, which I am, I generate them in blocks where I don't actually do the stats until after I take the differences. And so that's what we mean by common random numbers, running the same numbers into both to generate differences. And then those differences, those be the things that I'm going to replicate. So if I go to another replication, I have a new pseudo-random number seed, a new sequence of numbers. That sequence of numbers goes back into the same models, and that generates a new difference. And then this difference, whereas in the previous one, A had the higher value, now A has the lower value. So I'm going to get a bunch of differences. Some might be positive, some might be negative. And then my question is, do those differences, are they close enough to zero for me to conclude that there is no obvious difference between these? Or are they far enough away from zero that I can conclude that A is better than B or vice versa? So I'm going to get a table here where I'd say for replication one, it has this random number seed. I got this difference. Replication two, this random number seed, I got this difference. And I do that for as many as I want, where every replication is duplicated so that I get pairs of replications that generate single differences between those pairs. So the two models are related. They're blocked by these common inputs. And so from that, I can then again study the confidence interval of those differences and whether they're different from zero. So I guess maybe before I go on, are there any questions about CRNs? Clear what the idea is there. Okay, so then kind of the CRN analog for absolute performance measurements are antithetic variates. So here I have the exact same model, same shape model, same flow chart, everything the same between the top here and the bottom. I have a random number seed, generates a set of inputs or a challenge to A, which will generate a performance out of A. That challenge, I mean, the random numbers that are generated behind the scenes were all numbers between 0 and 1. Those are then transformed to the random numbers that you actually need to use in your model, exponential, Weibull, whatever. But behind the scenes, they start out as numbers between 0 and 1. So if I then subtract each one of them from 1, I get other numbers between 0 and 1. And those become legitimate inputs for the same simulation model to generate a new replication. And that will have its own performance, which will be different from this performance. And so if I average the two of them, this average is what we refer to as an antithetic variant. So it is an average of two outputs which are coupled together, so they're not independent from each other, similar to CRNs. Whereas in CRNs, we were hoping that the two models, A and B, would fluctuate in the same direction so that we could subtract off that common noise. Here, with antithetic variates, we're hoping the opposite. We're hoping that the two outputs from the same model will go in the opposite direction. So we're hoping that if this is an easy set of customers, this will be a hard set of customers. In many models, that will be the case, but it isn't always the case. And so we have to do pilot studies for both to see if they're going to work out. But in the ideal case, this random number seed generates a true set of random numbers, a complementary set of random numbers, which generates two performance variables, which you average. That is your antithetic variate. That becomes the thing you write down for this row of the replication. So then you do that again. So replication 2, new pseudorandom number seed, another set of random numbers distributed between 0 and 1, gives us another performance out. We do 1 minus those, gives us another set of random numbers, which gives us another performance out. We take that average, that's another antithetic variant. We do that over and over again. We get a table just like with the CRN case. And so for this replication, this is our average. For this replication, this is our average, and so on. And then we can use those to generate a confidence interval. And that will hopefully give us a tighter confidence interval on the absolute performance we're trying to estimate out of this model. So that's antithetic variance. So in some ways, very similar to control variance. On a final exam, you might imagine that I will give you a list of random numbers, numbers between 0 and 1, a sequence of them. And remember, like on the midterm, I think I had at least a problem or two where I gave you a list of random numbers, and then I asked you to use inverse transform sampling to then draw either discrete or continuous random variates based on those numbers. And so you had to know that you needed the inverse CDF, and then you had to plug in the numbers into those inverse CDFs. You can imagine a similarly structured problem to these, where I might say, here's, here are a string of numbers, generate a antithetic variate, Gesundheit from, and then I would give you a very simple sort of simulation analog, where you'd have to kind of know that that means that I need to plug in not only the first random number, but then also 1 minus it, which I won't give you. And then you plug in both of those into a kind of model sim. And then that will give you two numbers, which then you'll have to know to average. So, knowing how you would manually do this kind of exercise that I just did here, starting with a list of random numbers. If I were to ask you to sort of generate a CRN, like generate um, a, um, a difference from a CRN or generate an antithetic variate, that would be sort of, that's kind of an example of a type of question I could ask about these. It's kind of more quantitative. So any questions about those CRNs and AVs? They're very closely related. They're easy to get confused. CRNs, the R, think relative. I know R is for random. AVs, A, think absolute. So R is for relative, A is for absolute, if that helps. Okay. So yeah, each measured average is a variate because it's a realization of its own random variable. And then again, hopefully the AV has less variance. Okay. All right. Skip that one for now. All right, then importance sampling. So importance sampling is an interesting topic. It's always impossible as an engineer to get rid of all failure in your systems. Eventually, your systems will fail, and the question is, how often does it fail? The whole idea of Six Sigma design is is both, do things fail rarely enough, but also do they not fail too rarely? So, the idea is that you've got manufacturing parts that are coming off the line. For every million you get, you're going to get a certain fraction of those that are failures, and you want that to be relatively small so that you don't waste. But you also, if you have a really, really a good manufacturing line that produces absolutely no failures, then you could also ask the question of how much money could I save by, maybe there's a reason to increase my failure rate. It's always the kind of, Henry Ford had the famous quote. Supposedly, I don't know if it's actually a real quote. When he looked at the Model T, they had all these Model Ts in junkyards that had broken down, and they asked people from Ford to go and look across all these Model Ts to find parts that were never broken across all of them. And they found that there are certain parts that just never failed. And he said, okay, go and weaken those parts because we have over-engineered those parts. They outlive the life of the car. If none of these cars ever died because that part died, then there's no reason for us to spend the money to engineer that amount. So you can go either way. But regardless of how you feel about that, it really is important in the engineering process to have a way to estimate failure rates. And failure rates are necessarily low for good systems. I mean, there are some systems that maybe fail more often than others, but theoretically, systems, this desk, a car, physical systems in the real world where people could be in harm's way if they fail, it's likely that they fail very, very rarely. So it's important to estimate the failure rate, but it's also very hard to estimate the failure rate. So, and if it's a very complex system, we probably need something like a sim. Like it's not going to be a back of the envelope calculation. So that's where importance sampling comes into play. And so, this is just some sort of my favorite kind of examples here. And unfortunately, a lot of them come from Samsung. I think they're bad at this. But so, like, this is a few years back. This was a washer that Samsung made, a top-loading washer that it turns out that there are some fasteners across the top that would fail. And so when this thing would be up at top spin, sometimes it would get a little bit of an up and down movement. It would pop its top off, and the drum would go shooting out of the unit. And here you can see where it's hit a wall here. And it injured people. I mean, people would be like, "Oh, wow, my washer's walking. Maybe I'm going to be here to see if I need to make sure." And then it would pop off and like would hit people who were standing above it. So this was not only like damaging, destroys the unit, it damages property, but it also damages human life. So this was an example where this is always possible with a top loading washer. I mean, there The only thing that's keeping those drums from popping out are these things that are securing the top onto here. So it's always possible that these things are going to fail, but hopefully it's really, really, really rare. The problem with Samsung in this particular case is it was not very rare. I mean, it was rare enough that if you ran 100 of them, in a factory somewhere, maybe would never happen. But once you start selling millions of these things, then it happens an appreciable amount to the point where it gets a lot of press. And unfortunately for them, so here's an example of the press for that. So they had to recall a bunch of these. It was extremely costly and was bad PR, especially because it happened around the same time as this for Samsung. Certain phones from Samsung, in particular the Note 7, became well known for their lithium-ion batteries just catching on fire in people's pockets. Just I think a week and a half ago, there was I think a plane in Texas where I don't know if it was a Samsung phone in that particular case, but someone's phones caught fire in their pocket, gave them significant burns, and then there was a lot of smoke inhalation issues with people around them. They had to evacuate the plane. And for a while, if you tried to board a plane with a Samsung Note 7, they wouldn't allow you to board the plane. And so this was an example where there were rare cases where these lithium ion batteries, because of their suppliers or whatever, that they just misestimated the failure rates and shipped these things probably too soon. And then once you've got an ensemble of a huge number of replications in the people who bought these products, and they're testing them for you. And you find out, oh, the failure rate's a lot higher than we expected. So now they're doing the high number of replications that they couldn't do back when they were estimating this. It's not only Samsung. So this, Boeing has had a lot of problems lately. I could even update this with, the door plug issues. But this was, I think, a nice one because simulation actually predicted this. But then managers and marketers ignored that information. And as someone who's worked in industrial R&D, then I can tell you it is very frustrating because it's not just these sorts of things, but if you ever go and do R&D work, you will design these red, yellow, and green features. So features that definitely have to ship on a product, and it'd be nice if they were available, and if we got these it'd be great, but we're not at all thinking we're going to get these. And you might manage to design all of these features into it and have a great product, and you think it's going to ship the next year, and then you find out that once you submit your design specs and everything's up there and all your reports, you find out somebody in marketing has decided to spread your product out over the next 15 years. So you find out that they're going to take this card that you built in electronics and then just not populate certain parts of it. And then next year they'll populate some parts. Then next year other parts. And that way they can sell upgrades. So you design something that's ready to go right now, but the thing you designed doesn't actually get sold in its full complement until 15 years later. And so that's the state of the art. Like, that's why we have so many technologies like in the academic sphere that are not in the consumer grade because marketers get in the way and they slow that down. And so, similar, it sounded like similar sort of management pipelines got involved with Boeing, where they made some hardware changes, which required some software changes. And so this vehicle, this plane, it had a flight controller that would adjust the angle of the plane in ways in which the pilots didn't know were happening. And so what you would end up getting is under certain conditions, because of the movement, the change in how the sensors were used, the computer would compensate for this new sensor use by automatically moving the plane in one direction. The pilots would think that was a malfunction. They would correct, and then these two systems would fight each other, the pilots and the plane. And that led to some catastrophic failures, that led to crashes. And what is crazy about all of this, and I think I have a slide about this maybe, is that they actually had exactly these failure modes come up in a flight simulator. And so they did sim this, and they said, wow, if you didn't know this was going on, you could get into these cases here. And so that was discovered in simulation, but then those reports eventually were not passed all the way up to decision makers, or decision makers decided that this was too rare for them to worry about. So again, an improper estimation of how often this rare event would occur. And that led to catastrophic. Not there's huge losses of life in the short term and in those families, the long term of those families. But then, this started, a spiral, I think, of really bad reputation for Boeing, which I think they're still feeling today. And as they get more and more of these errors, which some of them are quality control errors for sure, but in this particular case, this was a predictable flaw in the design that was caught, but then they just, misestimated how much of a problem it would be. So SIM can help with estimating rare events. It still counts on people trusting the people. That's why communication is so important. That's why you not only have to become a good simulation engineer, but you have to also have a way to somehow communicate. You can't just say that, oh, all the Jacobians are negative or something like that. Like people won't understand that. So you have to find a way to make compelling cases as well. That's why we not only have you do sim in this course, but we cap it off with you doing a report. It's not just us finding busy work for you to do at the end of the semester. Really, sim, like science, doesn't exist until you disseminate it. And if there's no one there to listen to your reports, you may as well just have not done the sim. So rare events are important. How do we estimate the frequency of these events in sim, not reality? And how do we trust our estimates without running huge number of replications? So I hope I've motivated you that if you deploy your product to millions of people, that will be a huge number of replications, and they will properly estimate how frequently these events will happen. We would like to not have to use millions of replications, and especially not millions of real replications. So what do we do with that? Well, we can say is, for any sim, its variation on the output is generated by variation on the input. So we can stress test sims by saying, let's look at the input models going into the stochastic simulation. Most of the time, those inputs are within some range, but there are inputs that are rare, but they could happen in the system, and these may not be causing the failures, but likely if we are to hit the system with these inputs, it will be more likely to generate failures. So we can do this in sim with playing with random numbers, and then in real life we stress test things by putting them in ovens or by operating them while they're being shaken. So people like cars, there are giant machines which you can raise cars up to, and they can operate them while they're shaking the tires as if they're running for hundreds and hundreds of miles through rocky terrain that particular vehicle will never drive through. But the idea there is not to see how far it can drive through rocky terrain when it wasn't designed that way, but it's that if we can maybe the rocky terrain will end up stress testing the vehicle so that we can see what things are going to break when they break. So we may not be able to properly stress test it on a normal road, but on an abnormal, bizarro road, then we finally will sort of exercise the demons in that car to finally see what are the weak points in that car. And that's the same thing we're doing with simulation here. So we find an input or set of inputs where we are going to overrepresent a portion of that is rare, but we think stressful to the sim. So if we shift from here, where it's centered around 0, to here, where it's centered around whatever 2.5 or so, we're sort of, it's this stress testing is by loading these dice up. So we go from fair dice to loaded dice, so that hopefully we can get more of these rare events out. But then after we do that, we have to then this is our depiction of our likelihood function, our W function, is this idea that if we do get a lot more of these catastrophic events out of our sim using this stressful input, to then figure out how often that occurs in real life, we need to sort of multiply these outputs by, we need to sort of scale them by how often they occur with the stressful input, and then multiply that by how often that stressful input would occur in real life. And so that rescaling helps us take the extremely frequent catastrophic events in this world and turn them back into the rare events of this world in terms of bookkeeping. And that's the essence of importance sampling. So I think I've got this example of this. If you've got all of these are the same simulation. So this is absolute performance estimation, basically, same sim. And I've got a certain number of replications going into that sim. So this is a certain set of customers or whatever going into each one of these sims with certain performance measures, and all these performance measures within their normal range. So this is typical input data. So what I'm going to do is that in order for me to get outputs that are not very typical, then I'm going to put pathological input data in. So I'm going to draw from a new input distribution. So this input distribution was S. This input distribution, this pathological distribution, I'm calling G. And notice that in this case, it has a very different distribution. So in F, these were all above 1, like between 1 and 10. Here, these are all pretty small. So these are not normal inputs. So these might be inter-arrival times. So here, customers are spaced sometimes 1 minute, sometimes 5 minutes, sometimes 10 minutes apart. Here, all the customers are arriving right on top of each other. This is really stressful for whatever this queuing process is, for example. And so that's going to give me performance measures, some of them which look in the typical range, but a lot more often, some of these performance measures, which might be wait times, queuing wait times, are going to be really long. And so if I'm interested in how often do I get wait times greater than a half hour, well, it might have been in the previous case here, they're never greater than a half hour in the few replications that I run. So I would have to run a ton of them to finally get those rare half hour, and then a ton more to actually get a good estimate of how often that occurs. Here, they're happening almost every run. So that's great. Now I can say in this bizarro world that if all my customers arrived on top of each other, then I know how frequently I would get these long wait times, these long queuing times. So that's good, but then I still have to translate that back. So what I'm going to do is for every pathological replication, I have a pathological output. I say, is it interesting or not? So let's say it's greater than a half hour. So this is interesting, that one's not, this is interesting. So then I scale each one of those by this likelihood ratio. So this is how likely would this input, these little inputs happen in the real world, divided by how likely would they happen in the really harsh world. And that's going to be a number that is going to be far less than 1. So that will change this 1 to a number far less than 1. This will still be 0. This will be a small number as well. And then if I end up generating confidence intervals from this estimate of probabilities here, then that will end up being a good estimate of how often these catastrophic events will happen in my real system. So that's the idea behind importance sampling. Stress test the system and then normalize the outputs by how typical your stressor is relative to the real world. All right, so are there questions about that, importance sampling? Okay, so then the last one then is control variates, which we could apply to any data set really. So we've got 2 simulation models. They're very different. This has one flow chart. This has another flow chart. I'd like to know the difference between these two, for example. And so they both have uh, an important real world input X that is different to control but easy to measure. So in our power plant example, it was temperature, but they both have this variable coming in. They aren't necessarily the same. So they aren't the common variable, but they're measurable. So whenever I run replications of A, I might get some values of this variable. Replications of B, I might get other values of this variable. But the key point is that I can measure this variable going into A and B, even if I can't control it. And I can generate statistics for this variable. I know maybe the average value of this variable. So so then I've also got my input into the systems that may be easy to control, and that is like what would have for CRN. So I've got the things that I have access to that I can control, and then I have the things that are not uh, easy to control. And both of those produce variation in my output. And so, whereas with CRN, I subtract off the common variance here, with control variates, I try to subtract off the amount of variance due to this uncontrolled version here, this thing that I can't, that is different between these two, but is measurable. So, so I'm going to try to compare the each X with the, and this is supposed to be X bar, but it looks like it hasn't rendered in PowerPoint across the projector well, but this is the average value of X. So if I take X versus its average value, then I can know that, is this 10 below average or above average? Is this 11 below average or above average? So now I can know that for this model A, it had a below average temperature, and this might have had an above average temperature. And I can then use that to hopefully get a better idea of whether the variation on Y is due to actual differences between these models or due to this uncontrolled input. I can also do that for absolute performance, and it's maybe a little easier to understand here, where I am just trying to say, I've got a single model, and I'm just trying to estimate what is the average output from that single model. And some of that is due to the system, and some of that is due to external variations. So I've got a known mean from my input model. So on average, there's 5 minutes between every customer. But it might just be that for this system in its replication, that it got lucky and it was only 2.5 minutes or 2.3 minutes between every customer. But with this one, it might have got lucky and it was only 6.5, and it was unlucky and it's got well, actually, I guess this would be the lucky one. This had more time between customers and this had less time between customers. So this traffic was a little busier than this traffic. In the law of large numbers, they both would have an average of 5. But for my simulation replication, this was sort of an unlucky sequence and this was a luckier sequence. And so I can then say, well, based on how unlucky this is, does that explain some of this variance? And based on how lucky this is, does that explain some of this variance? And so I can hopefully control for that by subtracting off the difference between this and its average and using that to adjust this output, and subtracting off this and its average and using that to adjust this output. So that's what we're going to do. So so I've got my statistics of my X. I've got information about X. I've got information about Y. I want to alter Y using what I know about X. So I use this formula here where I take the Ys that I can measure off every replication. I take the X's that I can measure off every replication. I take what I know about the mean X's, take that difference between the input and its mean, and then I use that to subtract off a portion of the output. And that gives me my new control variance, which is hopefully the thing that has less variance than that output. So Z is a random variable itself. It's a control variant. If I do a little calculus, I figure out the best choice of C is basically the correlation, the covariance between X and Y divided by the variance in X. So if X is very variable, then this is going to be small. If X is not that variable, this will be large. If there's high correlation between X and Y, this will be very large. If there's low correlation, then this won't do any harm, but it won't help either. So I do all of that. So there's my formula there. And so and then we can kind of say, well, where does this come from? Well, this portion here is basically a z-score of how bad the input is. So this is the input for this particular replication. This is the mean input. This is the standard deviation of all possible inputs. This is how bad the input is, or how good, depending on how you're scoring these things. And so that z-score gets then filtered by effectively a measure of correlation between input and output. So if Y is highly correlated to X, then a large z-score on X will subtract a large amount from Y. If X is not very correlated from Y, then it doesn't matter what the z-score is here. because this will end up not, subtracting off, and basically z will be equal to y. So that's kind of where this control variate comes from, is calculating how variable the input is and how correlated the input and the output are. So what we can then do with that is this process where we measure the statistics of the inputs, we measure the variance of the inputs, we measure how much the inputs and the outputs covary. And if we have all of that data, we have enough to calculate this. So you theoretically can do this with any data set, and you can do this after you run your sim, as long as you've stored enough data on the input. So as long as you have enough data on the input and you have all these data on the output, then you don't have to remember to do this ahead of time. You can always do this after the fact. And it will look something like this, where you've got all of your replications. For this replication, this was my average time between customers, for example. This is my average wait time or something like that. So after k replications, I can look at this x column and I can say, well, here's my mean, here is my variance, and then between x and y, here is how much they correlated, my covariance. So once I've calculated that, that's enough for me to generate my control variate. So in the control variate, notice it's just the output minus this value, this 22.7291. That is constant across here because that's that C value that is the optimal scalar there. Here, this is my input value minus its average, which is down here. So then this here is that variance, which is down here. So again, this is just the same formula we had from that previous slide. Y minus C times x minus e to the x divided by variance in x. That's my control variate. So I calculate all of those out, and then these numbers will have the same mean as these numbers, but they might have less variance. And that means that a confidence interval from this column will estimate the same thing as a confidence interval from this column, but this confidence interval will be tighter. And so that's the idea here. So there's a confidence interval calculated from this column. Here's a confidence interval calculated from this column. So if I'm trying to see if, for example, is the output equal to 0, that's my null hypothesis. Well, here I don't know because 0 is included in the confidence interval. But here I do know that P is less than 0.05, so that because 0 is outside of the confidence interval. So that's the idea here, is that because I've reduced the variance, I've tightened the confidence intervals, so now I can make more conclusions about which hypotheses can be rejected. So that's our last VRT, control variates. So any questions about that process? Okay. All right, so let's do one more of these then. So multiple choice, which variance reduction technique, VRT, generates inputs that are purposely biased to greatly increase the number of normally rare output events? Is it A, common random numbers, B, antithetic variates, C, importance sampling, or D, control variates? Okay, so we've got sort of a distribution here where the largest, the mode here, so about quarter of students chose B, about 60% chose C, and about 10% chose D. And so in this case, this is about stress testing. And so stress testing is about highlighting events that are particularly important to you. And so I was looking for importance sampling. So that's what I mean by importance sampling. All the rest of these sample the system under normal conditions. So they're just sampling. But importance sampling purposely biases so we don't care about normal events. We're only going to run sims of the important events or the events we really care about measuring. So that's what I'm looking for is importance sampling. All right, so before we then do kind of then a kind of a going back to kind of bigger picture things about SIM, any questions about any of that, about those VRTs? That's our review of VRTs, which is the last kind of strongly technical topic of the course. Okay. All right, so just as a reminder, we've been working with discrete event system simulation, process-centric sim. The main focus of this class, I always have to remind myself, which class I'm going into because I teach classes on all of these types of sims, or I have, but there are a wide variety of simulation modalities, and depending on your application, sometimes you use one over the other. They have strengths, they have weaknesses. And even within one modality, there's a lot of different tools. And so most of the tools on here are primarily for discrete event system simulation. A few of them do other sim as well. Like, AnyLogic, for example, this is a tool that is made for all three. It's not that great at agent-based modeling, but it's pretty good at both discrete event system simulation and system dynamics modeling. VinSim is designed for system dynamics modeling, but you can do discrete event system simulation in it. And so even the tools have their pros and cons. And the people who sell these tools will, make them sound much better than they are. You go into different companies, and companies will have licensing agreements, and you'll just be stuck using that particular tool. We've, of course, been using Arena. It definitely has its pros and its cons. Arena is not that different from Simio, Simulate, and so when you go out into the world, you might find that the particular company that you work with uses Simulate or Simio or FlexSim, and you think, oh shoot, I learned things in Arena. It Within a day, you can find anything that you've learned in Arena, you can very quickly find in these tools. There's not a lot to them. You're like, how do I create entities? Okay, so I find that here. How do I generate, what are resources called in this tool? Where do I bring entities and resources together? A lot of these are designed with flowcharts in mind. Even in Arena, you can actually draw your flowchart in Visio and import it in those different ways. And other ones of these tools have that ability too. So there looks like a lot of diversity, but they all do the same thing. They're all getting at the same thing. They all have their strengths and weaknesses. Generally with whatever sim you're gonna be building in whatever framework in any language, you're always going to follow these sorts of steps, which hopefully you've started to see a little bit of in like your final project. So you have to formulate a problem, select objectives, conceptualize how you're going to build a model to meet those objectives, and then data that you're going to use to make that model relevant. Translate it then into a computer model. So this is on paper or in a non-sim tool. This is actually going into the sim tool, and then run your sim the first couple of times to see if it even looks like it's doing the right thing. And if it is doing the right thing, then shape it so that it is doing the right thing in the right spot. So verification is making sure that you didn't code something wrong. Validation is calibrating it so that it looks more like the real system. And then finally, you can use it as a proxy for a real system. So then you do an experimental design. And whether you're doing an agent-based model or a system dynamics model or a discrete event system simulation model, a process-centric model, it's a very similar experimental design. There are some tools that have, like system dynamics models generally don't have variability on their outputs. So you don't have to worry about the number of replications, but you still have to think about what types of inputs am I going to use to generate these outputs? And those are the right types of inputs. What sliders am I going to move around and so on? So then, you have to run those things. And if you didn't do your experimental design well, you might have to run way more replications than you need. And it might take a very long amount of time. You're going to generate data. And then, you have to analyze that data. And if it's data with variability, like it is in discrete event system simulation, it might involve some stats, sophisticated stats even. But then from that, you've got to do this, and I've emphasized this before, documentation and reporting. So you're just like in that Boeing case, they had some beautiful simulation work, and they had people that analyzed and predicted exactly what was going to happen. And yet somehow those reports didn't manage to communicate the seriousness of that problem. So was that the problem of the simulation engineers, or was that the problem of somebody who received that, or was it shared? That's a much more complicated issue, but it does show that none of this matters if you can't do this. And so when I was coming out of undergrad and taking my first engineering job, I was shocked at how much writing that I had to do. There was like a large, like nothing that I did was worthwhile unless it ended in a Microsoft Word report that had to be submitted to my boss and then his boss. So, really important there. And then finally, if you've managed to get their attention, then implement. And so, actually go and educate the pilots about this system and so on and so forth. So that is going to be the case everywhere. And your model will, somebody's going to ask, well, your model, it left out X or Y. And you have to be able to eloquently communicate that your goal wasn't to include everything, that your goal was to be illuminating and useful. You would have to always ask, well, what do you think would change if I would included X or Y? Do you think that would have changed these results in a qualitative way, in a quantitative way? Do you think we have data on X and Y that would actually, if I add this in, is that going to give me false assurances of certainty that I've added this in when I don't have good input models for these X and Y? It might be better for me to implement X and Y as random noise being added to my system than it is to actually try to build an X and Y that I have very little confidence that I know how they're working. So, it's never a goal to build a model that's perfect, and that's what I hope you take from this here. I hope you see through the labs and then this final project, it's not easy to build models, and especially convincing models. And so you might start the beginning of this class saying that a good simulation model has to include all of these details, but when I actually ask you to do a final project, then I think you would not like it if I came back and said, "Oh, well, you forgot to simulate, whether the lights are going to fail in your simulation of the factory." Like, well, if all the lights just turned off in the factory, wouldn't that affect their performance? And you'd have to come back to me and say, "Well, that's really a rare event, and that's so weird that I don't think we should make operational decisions based on this rare event that all the lights in the factory would just turn off." So those are the types of things that when you go into a sim, you think, oh, wow, that's something that could happen. I should probably build that into the sim, at least make it an option. But, you know, it's that may not be the best way to make the most useful sim. So hopefully that's clear. So looking forward, that's kind of the big message that I want you to take out of any sim class. Again, the timeline, today's wrap-up lecture here. We've got still the TA is available for project questions. Hope you have a happy Thanksgiving. Then we've got the final exam review. So no new material. It's just going to be highlights for this. So come with questions. And if it's all questions, that's fine. Otherwise, I've got, similar to the midterm review, a set of, just samples from a slide deck, which is sort of as kind of greatest hits from things after the midterm. And then if we get to it, then I've also thrown in stuff before the midterm just as extra review, but we'd focus on the stuff after the midterm. And then, of course, the near presentations. So I'll be making available that Perceptive, which is new for me. So I'm still a little nervous about it. So that, there might be some audibles called at the last second here about how this is going to work. But generally speaking, you're going to some, although the peer review stuff has got a little bit of uncertainty that I'm working out, the presentations, virtual video recorded, You can, if you want to be all on Zoom, recording it that way. If you want to be in the same room, recording them another way. If you want to be using PowerPoint's record feature and you're just doing audio over the slides, it just has to be like, is this the most compelling way to do it? If you want to break away from a slide deck in the middle of your presentation and open up Arena and do a live demo, if you want to play a video of, because Arena can record videos, or you can also, do screen caps and things. There are a number of different ways you could do it. So the presentation is sort of, it's very open, but it should be compelling, and it'll hit all the points on the rubric, and no longer than 10 minutes. Uploaded to Canvas, and then your report, again, 4 pages, excluding a title page and appendix, also uploaded to Canvas, then your peer reviews. And then the 2-stage exams. So again, stage 1 will be next week on Thursday. I will be here. You don't have to be. It'll be open at least Wednesday, Thursday, Friday, seriously considering Saturday and Sunday as well. Stage 2, Monday through Friday. You get 90 minutes after you start this one, 75 minutes if you do it here. Here, this is open and you can submit multiple times, but only your latest submission will count in this one here. So that's everything going forward. So before we do the last clicker for today, are there any questions? And then, yeah, I guess course evals sort of supposed to tell you that those are available. I think they disappear. They always disappear on weird times. I think it's like Thursday, not Friday, but Thursday of next week, I think. Okay. So with that, then I will ask this last multiple choice. And that's all I've got for you today. So get out a little early, and I hope you have a nice Thanksgiving break.